Finding a room temperature superconductor remains the central objective of condensed matter physics. It would completely eliminate electrical resistance, transforming power transmission and computing. In 2019, a major claim emerged. Sulfur hydride, when subjected to extreme pressures, supposedly achieved a high-temperature superconducting state. This chart shows the foundational proof for that claim. In panels A and B, clear downward slopes in AC magnetic susceptibility appear at 38 Kelvin and 55 Kelvin, interpreted as the onset of superconductivity. This drop is widely accepted as the signature of the Meissner effect, the point where the material expels magnetic flux. But breakthrough claims in this field require more than peer-reviewed charts. They require an independent forensic look at the underlying raw data. The central question of this investigation is simple. Are we looking at a historic phase transition or a measurement artifact that was never removed from the data? To understand how an artifact could masquerade as a discovery, we have to look at the experimental environment. These extreme pressures are created using a diamond anvil cell. The actual sample being tested is microscopic. It is isolated between two diamond tips and surrounded by massive metal gaskets and a support structure. This creates a massive signal-to-noise problem. The magnetic response of the heavy experimental apparatus completely dwarfs the signal coming from the tiny sample. Isolating the true signal requires a mathematical extraction process. The final clean charts are the result of subtracting the massive background signal from the raw measurement. Because background noise is so dominant, a minor unrecorded fluctuation in the environment can distort the math, creating a slope that mimics a physical event. In extreme pressure physics, the data extraction protocol is the most vulnerable point of the scientific claim. The standard protocol derives the final signal by taking the raw data and subtracting the background signal. This background is measured separately at a pressure where no superconducting transition occurs to establish a baseline for the equipment's behavior. This method only works if all other variables, most notably the heating rate, remain identical between the raw run and the background run. This heating rate is defined by the parameter delta T. The research protocol specifies that temperature should be increased at a constant rate, approximately 0.1 Kelvin per minute. The protocol assumes that the temperature sensor and the sample heat at a smooth, constant pace without interruption. If the heating rate fluctuates during the raw data run, it will create a change in the slope of the raw data that the background subtraction cannot erase. Essentially, if delta T is not constant, the resulting subtracted signal is invalid. To verify if the heating rate was actually constant, we have to move past the published charts and examine the time-stamped data logs. Under a constant heating rate, a temperature versus time plot should be a perfectly straight line. When we check the logs for the background signal, they behave as expected, showing a smooth, constant slope. But the raw data logs for the alleged superconducting runs show a distinct, sharp break in the slope. Crucially, this anomaly occurs at the exact temperature where the superconducting transition was reported. This break indicates that the heating rate abruptly changed speed in the middle of the experiment. The discovery appears to happen exactly when the measurement equipment experienced an unrecorded structural instability. To see the scale of this instability, we need to focus on the temperature change between each individual data point in the logs. Mapping the delta T step changes reveals a sudden, massive vertical leap in the heating rate at the reported critical temperature. In the 117 gigapascal and 130 gigapascal experiments, the system suddenly accelerated. This means the system was heating at a wildly different rate above the transition point than below it. This behavior directly contradicts the author's stated experimental protocol of a steady, constant sweep. The alleged Meissner effect drop perfectly overlays an undocumented equipment anomaly. One might argue that the material's specific heat jump during a transition caused this sudden temperature change at the sensor. While specific heat does change during a phase transition, the physical scale of this experiment makes that explanation impossible. The temperature sensor is located approximately 1 centimeter away from the microscopic sample, where it is measuring a much larger thermal mass. The sensor is tracking a volume tens of millions of times larger than the sample itself. A microscopic change in the heat capacity of the sample cannot violently alter the reading of a distant macroscopic sensor. The temperature jump is an external equipment artifact. meaning the derived magnetic signal is artificial. We can test this by applying a forensic correction. What happens to the signal if we correct the temperature scale to match the steady protocol? We can recalculate the results by assuming a constant delta T step, rather than the anomalous jump found in the logs. Figure 10 contrasts original temperature steps in black with a corrected constant scale in red. With this constant rate, the raw data kink disappears. Applying this to Figure 11, the susceptibility drop vanishes. The transition was a mathematical byproduct of an artifact. Without the equipment noise, there is no evidence of superconductivity. The reported definitive signature of the Meissner effect was built entirely on a foundation of uncorrected measurement artifacts. We must finally ask if the alignment of the equipment glitch and the susceptibility drop could be a coincidence. A high-resolution overlay precisely matches the temperature breaks with the susceptibility kinks. The alignment of these events is mathematically inconsistent with chance, matching to better than 1 part in 1,000. This level of correlation indicates direct causality. The measurement error created the signal. These 2019 AC magnetic susceptibility results do not support the existence of high-temperature superconductivity. This specific case highlights the absolute necessity of raw data transparency when verifying breakthrough claims in extreme conditions physics. True scientific progress requires verification of basic experimental parameters rather than reliance on process charts.